So yeah, a cycle in transverse wave talk is when one positive wave and one negative wave, so one crest and one trough happen, okay? We call that a cycle. This is the full wave. So when we talk about a wave, it's a positive wave and a negative wave, okay? Above and below the undisturbed medium, completing one full cycle. The number of these cycles that happens per second, we call that the frequency. The number of cycles or waves given per second is frequency. Now you have to like measure it, right? So this is like, pick a point, such as where the boat is, right? And count the number of waves that pass you per second, okay? If you get one wave passing you per second, that's a frequency of 1 hertz, okay? The unit for frequency is hertz, H-E-R-T-Z, abbreviated H-Z, capital H, little z. 1 hertz, 1 cycle per second. So if I said some electromagnetic wave had a frequency of 1 billion hertz, right? There's 1 billion waves per second hitting you, okay? Or more, right? Changing the speed of the wave changes the frequency, right? Okay. So for example, if you're being hit by 1 wave per second, don't worry about what the actual velocity is, how fast it's actually traveling. But if you're being hit by 1 wave per second, right? And suddenly the speed of those waves doubled, you're going to be hit by 2 waves per second. Yeah? The speed doubles with nothing else changing, you're going to be hit by 2 waves per second, okay? As well, the wavelength has an effect on frequency, okay? If you're hit by 1 wave per second, and then suddenly the waves don't change speed, but they get closer together, they get twice as close together, well, you're going to be hit by twice as many waves per second. Your frequency will go from 1 hertz to 2 hertz, okay? If you were able to start moving in the direction of the wave, yeah? So take your boat and start to accelerate your boat in that direction towards the wave, the apparent frequency is going to increase. The wave's not traveling any faster, but your relative velocities are increasing. Your relative velocity is increasing because now you're moving, okay? So changing the speed that the wave moves toward you changes frequency. Changing the wavelength changes frequency, okay? By the way, also, if this were real water in a real ocean, and you're really out here in your real little sailboat, okay, and that big old wave starts coming at you, what are you going to do? Let's say this wave is traveling this direction at 10 meters per second, okay? And you're in your little sailboat. Let's say you've got a little outboard motor that you can employ, okay? A little propeller, okay? What are you going to do? You're going to turn that motor on, right? And are you going to head toward the wave? You're going to head away from the wave, right? How fast do you have to be going to get away from that wave? Faster than 10 meters per second, right? So I start traveling at 11 meters per second, and I'm going to outrun the wave, right? Okay? If I go like 5 meters per second, the wave's going to catch me, right? But its apparent velocity will be slower. Okay? It's going to pass me not at 10 meters per second, but at 5 meters per second, right? It will have an apparently lower frequency because I'm traveling away from it. Okay? If I can outrun it, that's great, but if I can't outrun it, I can at least slow down how many waves hit me per second, right? So I travel away from the wave, right? So if you ever find yourself out in tsunami land, right, out in a little tiny sailboat, you're gonna ask yourself what went wrong, but then also you're gonna have to start moving away from that wave coming towards you, right? All right, excellent. Good morning, sir, to you. Okay, so you can hopefully you're starting to understand using the water analogy that there's relationships between frequency, wavelength, and velocity, okay? And there's going to be an equation that these things obey and follow. We're going to be able to like put down on paper some numbers and see how these things change, because you can sort of intuitively get it, yeah. But it's just as important to be able to put it down in a formula. Okay. Let me maybe try to help a little bit here. So let's see. So frequency, right? So frequency, remind you, is affected by the speed of the wave and the wavelength. Okay. So let's zoom in on here. These two waves are traveling at different velocities, but they have the same wavelength. We're assuming they have the same wavelength. They look the same to us, right? Which one are you going to be hit by more frequently? The one traveling at 5 kilometers per hour or 10 kilometers per hour? So, Marco, 10 kilometers per hour, right? So you're hit by, a wave every so often from the 5 kilometer per hour wave, and you're hit by exactly twice as many of the 10 kilometer per hour waves, okay? Frequency is affected by the velocity of the wave. Again, this is assuming you're stationary, right? With respect to the ground or whatever, yeah? If you travel in the direction of the wave, then you add your velocity to the wave's velocity, okay? So if you travel, if you start running, let's say this one here, right? You turn and start running toward this wave at 5 kilometers per hour. Will they now have different frequencies or the same frequencies? The same, right? Because if you travel towards this wave at 5 kilometers per hour, you're going to add these two velocities together. And your apparent velocity to the wave is going to be 10 kilometers per hour, okay? The same as this stationary dude, okay? So you're going to get a exact same frequency. They're going to hit you the same amount of times per second, okay? The same as if this guy were stationary, okay, getting hit by a 5 kilometer per hour wave, but this guy turned and ran that direction at 5 kilometers per hour, okay? Now they're going to experience the same frequency too. It's kind of exactly the same thing as what's going on over here with the boat running away from the wave, okay? The point I'm sort of trying to make in the background is that motion is relative. It's relative to other objects, right? You know that because you sit in your car driving stationary down the road, right? And you've got cars next to you on the freeway that are presumably to you don't look like they're moving very much, right? If they're driving right next to you on the freeway, you guys are going the same velocity. They don't look like they're moving, yeah? But then you look at the cars in the oncoming lane and they're zoom, zoom, zoom past you, right? They look like they're going way faster than they actually are because your two velocities are being added, right? Motion's relative to observers. That's what's secretly going on in the background here. The next thing is that two waves traveling at two different people, one wave traveling at 5 kilometers per hour and the other wave traveling at 5 kilometers per hour. So same velocities. The first wave has a wavelength. The second wave has a wavelength of half of the first wave. Okay, so if the bottom wave has twice as many waves per distance, the frequency is going to be greater. Okay, you will be hit by twice as many waves per second at the bottom versus the top wave. Why? Because the wave at the bottom, let's say, has a wavelength of half of the top one. Okay, so all this stuff, frequency, wavelength, velocity, they have a relationship, okay? So we can express this relationship mathematically as V equals F times lambda, which V is velocity, F is frequency, and this Greek symbol lambda, which is the letter L in the English alphabet, represents wavelength, L for length. So it's just a funny looking L. Don't let it weird you out. Okay, so there you go. There's the formula, okay? So if I want to figure out the velocity of a wave, what two things do you need to tell me? Yep, if you give me those two things, I can tell you the velocity. If I want to know the frequency of a wave, what two things do I need to know? Yeah, and if I want to know the wavelength? Yeah, absolutely. There's only three things, right? If you give me two of them, I can tell you the third one. Okay? Now, the catch is I have to know two of them. Okay? So if you get a test question, right, and it tells you to determine the wavelength of some wave, right, but only gives you the frequency and doesn't give you a velocity, well, then you know nothing. Okay? If it gives you velocity and not frequency, you also know nothing. Yeah? You need to know velocity and frequency to figure out wavelength, and you need to know two to figure out one of the others. Okay, any of the other three. All right, there's a couple of ways that you can play with this formula. I mean, to me, as long as you can remember this formula, you can in principle do anything you want, right? But there are some tricky ways to do this. Okay, some little mathematical kind of tricky ways to do this. For example, using the cover with a finger method, okay, cover the thing you want to solve for. So for example, cover lambda with your finger, and we see that frequency and velocity are directly proportional to each other. As well, if you cover lambda with your finger, you now know that frequency and velocity are the two things you need to give me. Okay? That's one way to think about it. The other way, which I actually kind of like, is the T-triangle. The T-triangle tells you what to divide into what or what to multiply by what. Okay? In the T-triangle, you put the velocity always on top. It never gets divided into anything. Frequency on one side, wavelength on the other. So this is telling you velocity is equal to frequency divided by wavelength. If you cover wavelength, wavelength is equal to velocity divided by frequency. If I cover frequency, frequency is equal to velocity divided by wavelength. And if I cover velocity again, velocity is equal to frequency times wavelength. So you multiply the things that are to the left and the right, and you divide from top to bottom. Notice that the velocity is either by itself on one side of the equation, or as the numerator, the thing that does not get divided into. Okay. So let's do practice. Okay. Let's say standing on the beach. Okay. Standing on the beach, you get hit by a wave, and then 3 seconds later you get hit by another wave. And 3 seconds later you get hit by another wave. Okay? And the waves are 8 meters apart. So what two things have I given you?
Frequency is every 3 seconds.
So you have a frequency, and you have a wavelength. Okay? Frequency and wavelength. So, what is the wave's velocity? How fast is it traveling? Take a couple of minutes and try to work with that one. I'm gonna help you guys through it, but take a couple of minutes to try to work with that one, and we'll see if you guys can get it on your own. it's not going to be exactly that easy. So I'm going to see if you guys can do it. Take a couple minutes, and I will walk you guys through it. Keep in mind, the unit for frequency is hertz, which is how many waves per second, not how many waves per 3 seconds. So you're going to have to make a conversion before you move into the equation. I need to just double check my math. 8.33. Yep. Okay. Excellent. When you are done, or when you give up, just put your pencils down so I know everybody's done. All right. Okay, did anyone figure out the first thing to do? I gave it to you, 1 wave every 3 seconds, wavelength of 8 meters. Is it okay to have a wavelength of 8 meters and plug that into the equation? Yeah, because that's just our wavelength, okay? But in this formula, V equals F lambda, velocity equals frequency times wavelength. What are the 3